Okay, so 2-1. 2-1 introduces the first new calculus object that we're going to learn this year. There's only 2 objects that we're going to learn. This is the first one. So it is a derivative. So what is a derivative? There's all kinds of different ways to think about derivatives. We're going to think about them to begin with, mainly the tangent line. Is that all this big concept of a derivative is? No. It's just one of its possible uses. A derivative is this mathematical object that has just like this smorgasbord of different things you can do with it.
That word.
You like that word? All right. So we talked about how in order to solve a lot of problems, like Descartes was trying to solve problems, he needed the tangent to a curve, and he used the circle, and he went through that complicated process. Let's think about how we could do it another way. So let's just pick a specific function to illustrate this process of a derivative. Okay. Let's pick an easy function, like the easiest function we know.
Y equals mx plus b.
Favorite function?
Y equals mx plus b. A line.
A line's too easy though, because the slope of a line. Let's think about why I'm not going to use that. A line has the same slope everywhere, so the tangent line to a line is always the line. It's still the same line. What's the next easiest function?
X squared.
X squared. Let's look at that one. Okay. I'm drawing it big for a reason. We could do this concept with any function, any graph we could do the same thing with. I think x squared is a nice easy example though. Okay. All right. So let's just calculate the slope on several different intervals. Let's start with just on 2 to 9. Okay? So we'll go change in y over change in x, and we'll figure out what the slope is. So here's 2, 3, 4, 5, 6, 7, 8, 9. Okay? So first I'm going to calculate the slope of the line that goes between 2 and 9 on the curve. What kind of line is this? Secant line. It crosses twice, right? Our eventual goal was to create the slope of what kind of line? A tangent line. So we can see it's like right there, right? That's going to be that tangent line. But we're just going to start with this interval, 2 to 9. I'm exaggerating. So let's calculate the slope. What do we got? Change in y is going to be 9 squared, 81 minus 2 squared over 9 minus 2. So 81 minus 4 over 7. Is that right? Can you guys help me out with the calculator? Give me that decimal.
Yeah, it's not a decimal, it's just straight.
Is it 11?
Yeah.
Oh yeah, it is. Duh. Okay. So that's the slope of that secant line. We're going to use that as a very, very terrible rough estimate of the slope of our tangent line, which we know is this, right? So I'm going to draw the tangent line at 2. Could I do this in different places? Yeah, it depends what point they ask me to do it at, right? I'm going to pick at 2. That's our eventual goal, is to get the tangent line at 2. So I'm eventually trying to get that red line. That's good enough. That's the tangent. So a very, very rough estimate. Let's make it a lot better. Instead of on the interval 2 to 9, let's create the secant line between 2 to, what do you guys think? 3. Let's do 3. I'm not messing around. Okay? Change in y over change in x. Let's do it. So we get, you plug y in, 9 minus 4 over 3 minus 2 is 5 over 1 is 5.
I have it squared.
Oh, I did square it, right?
Oh yeah, sorry. You just didn't. Well, you didn't.
I didn't show it.
There. Okay.
I'm shortcutting. It's x squared. Okay. That's the slope of the secant line between here and here, right? Which is really close to that red line, isn't it? Let's see how good a job it did. Let's do it again. Decrease that interval again. do 2.2. So change in y, change in x. So we're going to have this time 2.2 squared. I don't know what that is.
4.84. 9 squared.
4.84?
Yeah.
So we've got 0.84 over 0.2. What is that? 4.2. Is that good enough? Anybody have a guess yet as to what the actual slope of the tangent line is? I would guess is 4. Are we very sure about that yet? You can see the slopes approaching something. I don't really see them approaching yet. So I think we need to pick the smaller interval even. Let's do one more.
2.001.
Ah, I like Cassidy. She's cutting to the chase. Calculate that slope, if you will. Do it yourself. I don't need to show you. So 2.001 squared minus 2 squared over 0.001, right?
Minus 2 squared?
4.001. Do we have confirmation? Is that exact or is it approximate? This is exact? Okay, and what else did you say, Cassidy?
It's approaching 4.
The limit is approaching 4.
But we could also try 2 in the slope of 1. To make sure it's approaching 4.
We could, that's a good point. But do you think that since this curve is like solid through there and it's continuous, I don't think we need to do that, but that's really good. If it was like, if it like stopped right there, we'd have to think about the limit from the other side maybe, right? And will we be able to get a tangent line if it just stopped right here? Think about the square root function. Is it going to have a tangent line at x equals 0? How do you draw it? You don't know which way to draw it. Okay, so that's a good connection to make to our continuity arguments. So we agree that we're thinking the slope of that tangent line, the red line, is a slope of 4. What did we do here? We just used the reasoning that we'd already built. We just created a derivative. Whether you
just
realize it or
start bigger
not.
and go smaller and smaller and smaller and smaller. But eventually
What
you
is
just
that
start
process
smaller.
of going smaller and smaller and smaller and smaller? A limit,
Standing.
right? It's approaching something. So we just decided that the slope of a tangent line equals what?
The limit of something.
The limit of something, I like it. The limit as, what are we going to put under here? I don't know. Something approaches 0, right?
As the tangent line
As
is
the
0.
What? X? Almost. What were we changing and making smaller?
The slope.
We were making
So-
this
okay.
smaller. First we made that to 3, then we kept bringing it in. Isn't that
Integral.
delta x? So it's the limit as delta x approaches 0 of what?
Of the score. The slope. Well, in this case, it's x.
In this case it's x squared, but
It's just
the slope of the secant line.
Why'd you do?
The slope of a tangent line is always the limit of the slope of a secant line. Does that make sense? We just took the limit, we created this secant, then we went, okay, make that secant, then we went and made it more secant. I didn't draw all those, right? Here's another secant. And then if we kept doing it, we would have had more secant lines, and they're getting closer and closer and closer to the red line. That's what that is. So here's something you might recognize. This guy can be expressed like this. We're going to say delta x equals h. Your book continues to use delta x. That's fine if you want to do it that way.
At this time, would you please release the cross-country team? Thank you.
Why do they use theta x?
Why do they use what?
Never mind. Why do they use?
I like h. I think you guys will probably get less confused if you use h. h is delta x. This we've seen before, right?
Yeah.
This is our difference quotient. The only thing that's different is before it didn't have
The limit.
the limit. So I'm arguing that this part is the secant line. This part is the limit. Limit of the slope of a secant line is tangent line. This is a derivative. Okay? So in our example, x was 2, so we calculated the tangent line. Tangent line's slope. For what function? X squared. And we did it at x equals 2.
So, but we could run that anywhere, right?
Yeah, we could have, definitely.
So,
So whether you see it or not, this is also the derivative. Where is that f of x plus h and that stuff coming from? H is this.
Such huge.
First we had h as this value, then we shrunk h down to that, then we shrunk it down even more, didn't we?
0.001. So h was 0.001.
Yeah, at one point h was 0.001,
And
so
then
we
x
took the
was
limit
2.
as h approached 0. Now what's this part up here?
So it would be 2.
Let's look at the original 2 points. When h was 7, this was f of x plus h. X was what? 2, and h was 7. That's the first y value. That's like y2.
Wait.
F of x was right here. That's like y1.
So on
The
our
change
last,
between them is h. You could subtract x's and go 9 minus 7, but what was that? That was h.
so on our last example, x was 2, and then h was 0.001.
Yeah, but you can't just think about it finitely, right?
I know.
You got to think as h approaches 0, this is the change in x, this is the change in y. This is just a slope. That's all that difference quotient is. It's a slope. Limit of slope gives you the slope of the tangent line. Limit of the slope of the secant line gives you the slope of the tangent line. So this little thing right here, which we won't be seeing for like this whole class. We're going to do it in one lesson, and then we won't see it again. But this is the theory behind it. It's really important. Really, really important. So this guy. We have all kinds of names for it. We call it f prime of x. And all these notations are real important, so you need to know them. We call it dy dx. We call it df of x dx. There's all kinds of different notations. Now think back. Why might there be different notations?
Because of the different mathematicians.
Different
that developed.
mathematicians that developed this. Now the question is, why don't we just pick the best notation? Well, the answer is sometimes one's a lot easier to use and sometimes the other's a lot easier to use depending on what you're going to do. Okay? So this gun, this is Newton's notation. That is called prime. This is the derivative of f of x, though. The way you say that. So I say f prime of x, it means the derivative of f at that specific point x. dy dx is from Leibniz. I prefer this.
What?
Leibniz. Gottfried Leibniz, the other guy who invented calculus. I personally think this is a lot more useful. It's a lot more versatile. It extends to Calc 3. It makes things a lot easier when you get to other variables. This guy's easier to use to begin with, though. It's more user-friendly, I think. So, but when you go to other variable land, this becomes really, really like abstract. It's much harder to use.
What was the last one?
This is really just a hybrid.
Because see, f of
This is
x
like a
is
hybrid.
y.
So this has the d dx and it also has the f, so it's kind of a hybrid question. So we're mainly going to use those two. Okay? So let's get down and do this here problem. So notice, that is the derivative at a specific point x. There is also a derivative function. We're going to talk about that too. Let's just calculate a few derivatives. So I'm going to do 2 today and 2 tomorrow. So here's some examples. So let's say they give us that function and they want us to find the slope, the tangent line at 1, -3. Okay? So let's do it. Okay, so I'm going to take the limit as h approaches 0. If you want to use the book's delta x, fine. I like h, it's simpler. But, so I'm going to go f of x plus h minus f of x for h. I'm going to do that. So f of x plus h is 2x plus h squared minus 5 minus 2x squared. Whininess. Yes, this lesson will take some time. This is a big homework assignment. But luckily, you don't have to do this every time this year. Don't worry. So I've got 2x squared plus 2xh plus h squared.
Wait, Mr. McGee.
Yeah.
That minus 5, that's like in parentheses, right? Because that whole, well, it doesn't have to be, but that whole thing's.
It's being subtracted. That's why I
Yes.
have the parentheses, yeah. You gotta remember, because otherwise you'll leave this as minus when it's not supposed to.
Wait, yeah.
Notice, when you're going through this process, we've done it enough to where I can tell you this already. The end terms, the f of x things usually always cancel. Like all those parts should cancel most of the time. They might not cancel right away, but they eventually cancel. This part's going to cancel with that. So what's left? Still got my limit. What other things are left? Can somebody help me? 4xh, yep. 2h squared. Anything else?
Wait, where is your h on the bottom here?
Mm-hmm.
Okay, it's there.
Thank you.
Okay.
It's still there. So I'm going to factor it out. Cancel that. Notice that's also a common step. Somehow, you got to get rid of that h on the bottom. Why? You guys tell me, thinking about limits.
You don't want to put
You can't
0.
put a 0 in the bottom, right? That doesn't work for limits. Now, finally, you've gotten rid of the problem and you can just plug in. So what do you get? 4x. So what is the 4x? We have a notation for this now. We can call it one of two things. We can call it f prime. This is the derivative function for this function. If this function is 2x squared, its derivative function is 4x.
What happened to the limit, Anna? Oh, okay.
That's why limit's gone, right? That went to 0.
I didn't realize that.
You're good.
Sorry, I was looking.
You're fine. I can also call this dy dx. That's the derivative function. Now, they asked us to do a specific problem with it. They said find the slope of the tangent line at 1, -3. So, the slope of the tangent line is f prime of what? 1. Use the x value. So what's the slope of the tangent line there? 4. Done. Can you create that tangent line? I sure hope so. Let's do it. Y minus y1 equals mx minus x1. Y minus -3. M is 4. X minus 1. So I'm going to end up with y equals 4x. -4 minus 3 is -7.
Why
That's
did
the
you do
slope of that
1?
tangent line. There's that tangent line.
Because it's the line is the x.
Why did I pick 1? Because that's the x coordinate for that point.
It just is there.
This describes how to do it for any point. It says for any x value. So if they give you a specific point, plug it in. You're done. If you go and graph this on your calculator, you'll see that. So let's do the next one on our calculator.
So
Let's
wait,
see.
what did you do to the left? Like your little blue writing.
I created the tangent line. They said just find the slope of it, but I just went ahead and created the whole line. Okay? I want to do one more example with you guys today. And we'll do this one on our calculator to confirm, like we'll look at it and see what's going on here. See if we actually think that it gave us the tangent line. No more circles now. So nice. So, the question you might be asking is there a way to get that 4x, that derivative, without going through this limiting process? Oh yeah, it's a very easy way to get it. I'm just not telling you yet.
Oh.
So let's try this one. Let's say we've got that function, and we want the tangent line through 9, 3. Okay, same problem, just different function, different point. So can you guys set it up?
Wait, so it says find the slope of the tangent line, that's what we're doing
Yeah.
again?
So we're going to find the derivative too. So we'll just find f prime of x, then we'll use it. So we can take the limit, h approaches 0. So why did I have you guys do those conjugates so darn many times?
Because you have to multiply.
Because
by one.
how many functions have square roots in them?
Way too many.
A lot of functions in the real world and in your text have square roots in them. And almost every time you have a square root in them, how do you find a limit like this? You use the conjugate, right? What do I multiply this by?
Square root of x plus h plus root x.
What?
Okay. So what happens? Cross terms cancel. The first term is what? X plus h. Minus or plus? Minus x. I heard Kate say. Okay. The bottom, we usually just left this, right? It's your choice. Todd says the x's cancel. Do we even need to go to the next step? What else cancels? Next step on the h's are going to cancel. You can already see that. Just be careful. What's on top?
1. So you're
Was it 1 or negative 1?
It was
Negative 1.
1.
This one.
I have no idea.
Just checking. You have no idea, Austin.
1 over 2 root x.
You need to think about this. If you cannot see that, then you need to take one step at a time and see, is it negative 1 or 1, or is there 4 left up there?
Oh,
Sometimes
yeah,
there's going to
okay,
be different
I
things.
see how it's
I wouldn't just be expecting this to always be 1. You just see what happened. Yeah, everything canceled for us. Those went away, so it was 1h over h, so it was 1. Sometimes it's going to be different. I'm just trying to save you. Okay. Now can we do the limit? I think so. I think our problem is gone, so we don't have to write limit. We plug in 0 right there.
1 over 2 root x.
And Caitlin says it's 1 over 2 root x. That is the derivative of the square root of x.
So that's f of 1x, or f, whatever, prime x.
F prime, thank you, Austin. So now our goal is to create the tangent line, and then we'll put it in our calculator real quick.
Isn't that, so that's the derivative, but, okay.
That's the derivative function. Now if you want to evaluate it at a specific point, they could tell us any point, right?
9/3.
So square root at 9, 3, we're going to go f prime of what, Austin? You help me. It says for the
9,
derivative, you
right?
plug in x, right? Notice, does our derivative depend on x and y? It just depends on x. In multivariable calculus, you can have a derivative depend on x, y, and z. It can happen, but we're not going to be studying
Is that when
kind
the
of
d
thing.
of x sub dy comes in? Because you have your x and your y.
It does. I will see something kind of like that this year, but not the full deal. Good question. Okay, so I'm just going to plug in. I get 1 over 2 square root of 9. That's 1 over 6. Not 5, right? I want to see 5 there. Okay, so that's the slope. Y minus y1. So I got y minus 3, 1/6, x minus 9. So that's y minus 3 is 1/6, x minus 9 over 6 is 3 halves. I am writing fast, right? Plus 3.
Where'd your 3 go, Mr.? Oh, because it's plus 3 halves. Never mind.
Where did it go?
Oh, yeah, I see.
Might need to do scratch work. Okay, so we've got this. Let's think about what this looks like as a picture and see if it makes sense, and then we'll put it in our calculator and I'll show you how to use your calculator to do some stuff. Okay, square root of x, you guys know what that looks like. What does it look like?
It starts with the origin.
Draw it in the arrow. Okay, we know it looks something like this. They asked us to find the tangent line at 9, 3, so 9, 1, 2, 3. Tangent line should be, let's just visualize it, should be something like that. Just guessing. Does that look like it could be 1/6 x plus 3 halves? Mine looks like it's plus 2.5 plus 5 halves, right? But does it have a shallow positive slope? Let's see, because that's just a rough sketch. Get your calculator. So we want to just put square root of x in, right? You have stats, but if you're plots off. Right, so my plots are off. I know because it says right there that my plots are off. They aren't bold. Okay, so we're just going to put the square root of x in. You could actually put the derivative function in too. We're going to compare those if that's okay. So let's just look at the square root of x and graph it 0, 6. There it is. Now let's go and calculate. Here's a way you can numerically calculate the derivative. Don't check yourself on this assignment. We'll be using this for various purposes this year. Which one do you think it is?
dy dx.
There we go. So this doesn't numerically take the derivative of everywhere and give you the function. It'll just give you 1 point. So what point were we interested in?
9.
X equals 9. So if you press 9, notice it like magically pops up and it puts that in for x. And it gives you 0.16666. Is that what we got?
Yes.
We got 1/6. That's 1/6. So you can use your calculator to come up with the derivative that way. Just at 1 point. Can it give you the function 1/2√x? It can't. Can some calculators do that? Yeah, they actually can. But those would not be helpful calculators to us. Okay, so let's graph our y equals tangent line. What was it? 1/6 x plus 1.5. Let's see if it looks right. I'm gonna make it bold. I'm gonna change my window from 0 to 15, and 0 to 5. Look like we did a good job. You want to see if it's at the right point, you can go second calculate value. What point are we interested in again? 9. Yeah, looks like right in the middle, right? That's where it's actually tangent to the curve. That's right. So this should be like kind of a magical process. Like somehow this derivative gives you the tangent to the curve of any function, at any point, anywhere, all the time. It might be hard to do in this assignment, but it's going to be easy, right? Okay.
That's all we're finding. Well, we were actually just looking for the slope.
So we're incredibly grateful to
The slope tile
came up with these.
Once you get like this, the whatever.
You just substitute in the
Plug
9.
in the x.
No, look.